This is the video for electron configurations for Chemistry 1. So yesterday we learned about orbital spin diagrams showing all of the rows, all of the lines or boxes showing all your arrows, really clearly identifying which box or which line goes to which energy level, which sublevel, making sure that if I have 27 electrons, I have 27 arrows. But imagine doing that for something like cesium or something like barium, which has 55 or 56 arrows. That's a lot of arrows, that's a lot of boxes, that's a lot of places for you to potentially miss one of your rules. So we can start doing a kind of shortcut. Instead of doing this full orbital spin diagram, we can kind of pull the arrows out and just use numbers. If I look at cobalt, so we're going to do this again for cobalt, in the 1s sublevel, I have two arrows. Remember, each one of those arrows represents an electron. So if I have two arrows, that just says that in the 1s level, I have two electrons. So instead of writing this with arrows, I could actually just put a 2. We could say that I have a 1s2. In 2s, I have two arrows, so there's 2s. 2. 2p has 6 sets of arrows. 6. 3s2, 3p6, 4s2, and when I look at 3d, I have 2, 4, 5, 6, 7 arrows there. So instead of having to write every single one of those lines, every single one of the boxes, every single one of the arrows, making sure they're all up and down, you can actually just use numbers instead of arrows. We call this an electron configuration. It's a shortcut version of your orbital spin diagram. Your superscripts, which are those exponents there, represent the number of electrons in the sublevel. And if you were to add up all those superscripts, you can identify the atoms. So 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18, plus another 2 is 20, plus 7 gets you to 27. And sure enough, the atom with 27 electrons is going to be cobalt, because 27 electrons, and knowing it's an atom means it's neutral, so it should have 27 protons as well. There is a single major huge disadvantage to this, and for us it's actually not a huge disadvantage. In fact, most chemists, it's not a big disadvantage. But you do lose some information, right? You lose the ability to distinguish between those two electrons. You lose the ability to distinguish between those 6 electrons, between those 7 electrons. You can't say, okay, the electron in the third orbital of the 3D sublevel. You don't have the ability to do that with such detail. It's quicker. That's the trade-off, is you lose information. Remember, this is another visual of the different sublevels, different energy levels, the different blocks, to kind of help you remember the even shorter way of doing spin diagrams. You know, if you have an element that's right here, you know you're going to have to fill everything up to that point before you can get to 3p. You can assume that your 1s is full, your 2s is full, your 2p is full, and your 3s is full, because the only way to get to that point would be to have every other energy level and sublevel that came before it full. That's what Aufbau's rule says. You have to fill everything below that energy level before you get to the energy level you're currently at. So remember, you can make that assumption if you can identify where the element you're interested in is located. So we have some practice here. I'm going to do 2 of them. The first one I'm going to kind of work out the long ways, then I'm going to show you kind of a shorter way to think about it, and then I'll leave the third one for you to try on your own. And I'll pause it. You can pause the video so that you can work it out, and then the answer will pop up here in just a second. Let's start with Li, because it's a pretty short one. Li has 3 protons, which means I'm going to have 3 electrons. If I were doing orbital spin diagrams, I'd have to ensure that I had 3 sets of arrows. Really easy. But we're not doing the full spin diagrams anymore. We're just doing electron configurations. We're doing a little shorter version. So we're going to kind of start in the same way 1s, 2s, 2p, 3s, etc., etc. You can keep going if you want to, but you really don't have to. And you're going to start filling. Well, I need to ensure that the total superscripts, the total of my exponents, adds up to 3. So 1s, well, I can fit 2 electrons there. So 2 of my 3 are done. There's 1 more. So I'm out of electrons. I have 1s2, 2s1. I don't need a 2p. I don't need a 3s. I can stop at that point right there, 1s2, 2s2. See how that's a lot quicker? I don't have to draw all the arrows or the boxes. It just saves me a lot of time. Let's look at a slightly bigger one. Let's look at magnesium. Magnesium has 12 protons, so 12 electrons, which means my superscripts have to add up to 12. Here's where you can get a little bit faster with it. If you can identify what energy level and block your element is in, it's going to speed up this process. When you look at the periodic table, go ahead and look at it, see if you can find magnesium number 12. It's in energy level 3, and it's in the S block, which means in order to get up to 3s, Aufbau's rule says everything that came before that has to be full. But I have to get up to 3s. That's where magnesium lives in the periodic table. So I know I'm going to have to use 1s, 2s, 2p, and 3s. I'm going to have to use everything before I get to 3s. And not only am I going to have to use everything that comes before 3s, everything that comes before 3s is going to have to be full. That's what Aufbau's rule says. You have to fill everything except for the last one in order to have electrons in the last one. Which means I can assume that my 1s is full, and it gets filled at 2. I can assume that my 2s is full. I can assume my 2p is full. Because the only way that I can get up to my 3s is by assuming that everything that came before it is filled up with electrons. Well, I've used 2 plus 2 is 4, plus 6 is 10, which means I have 2 left. Therefore, I have 3s2. I'm allowed to put 2 electrons on an s sublevel. So, go ahead and pause the video here for just a second. I want you to try to do nickel, Ni. See if you can figure out where it is located in the periodic table, what the electron configuration should be. So go ahead and pause the video while you work on that, and press the video to get the answer. Press play to get the answer. So here's what the full configuration for nickel should look like. Hopefully you identified that it's in the 3D block. You're going to need everything before 3D to be full. So 2's to all the s's, 6 to your p's. That is up to 20. The 1s2 all the way to 4s2. 20 of your 28 are used. Therefore, you can pretty easily identify that you need 8 in that final D block. So we've been talking a little bit about how the difference between, that when we say atom, we can assume that all my protons are equal to my electrons. In other words, I have a neutral element. So for phosphorus, if I have 15 protons, I have 15 electrons. But what if I have something that looks a little bit like this? P with a -3 charge up in the superscript. That tells me that I'm no longer dealing with a neutral atom. I'm now dealing with an ion, something whose protons do not equal the number of electrons. Now you learned about all the different parts of an atom, and you learned how to identify the number of protons relative to the number of electrons. If it's phosphorus, I know it has 15 protons. That's what makes phosphorus phosphorus. That can never, ever, ever, ever change. 15 protons makes an atom phosphorus. What can change is your number of electrons. Well, if I have an overall -3 charge, that tells me that I have to have 3 more negatives than I have positive. In other words, 3 more electrons than I have protons, which is going to change what my electron configuration looks like. With phosphorus, we'd have 1s2, 2s2, 2p6, 3s2, 3p3, right? Because I want to end with a total of 15. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 3 is 15. But when I start dealing with ions, that's going to change what my electron configuration looks like. It'll look similar, but it's going to be a little different. So 1s2 is still there, 2s2 still there, 2p6, 3s2, but this time instead of 3p3, let's check our math. I need to end at a total of 18 electrons, right? Because we're doing electron configuration. We're trying to figure out where all of the electrons in these atoms and ions are. So I have 2 in my 1s, plus another 2 in 2s is 4, plus 6 in 2p is 10, plus 2 in 3s is 12. Well, if I have 18 and I've used 12, that tells me I have to have another 6 in my 3p. So notice, same type of atom, but a different charge means I have to account for those extra electrons. So here we go, just as we've written on the last page, the last page, 1s2, 2s2, 2p6, 3s2, 3p6. I'm sorry, the thing got a little messed up here. Let's see if we can kind of fix that. There we go. Now, we know this ion has 18 electrons, but there's also an atom that has 18 electrons. Argon has the exact same electron configuration because it has the exact same number of electrons. In fact, ions, all ions, are going to have the exact same electron configuration as one of your noble gases, so one of those group 18 elements. Anytime you have an atom and an ion, or two ions that have the exact same electron configuration, we say that those atoms or ions are isoelectronic. They have the exact same electron configuration. Phosphorus and argon, phosphorus with a -3 charge, phosphide, has the same configuration as argon, 1s2, 1s2, 2s2, 2s2, 2p6, 2p6, 3s2, 3s2, 3p6, 3p6. Okay, so we'd say that argon is isoelectronic with phosphide, or phosphide is isoelectronic with argon. So I'm going to do one of these, and then you can pause the video and work the other two. Where I'm going to go ahead and do chlorine, and then I'll pause the video and you can do nitrogen and aluminum on your own. Chlorine with a -1 charge, chloride, well, has 17 protons, because that's what makes chlorine chlorine, but it does have an overall -1 charge, which means I have 18 electrons, which means when I add up all those superscripts, it's got to add up to a total of 18. So let's just start. 1s2, 2s2, 2p6, 3s2, 3p6. Well, we're probably getting pretty close to 18. Let's check. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18. Now I can ask, or I have to ask, what element would also have 18 electrons? What atom is going to have 18 electrons? That's going to be argon, because argon has 18 protons, so when it's neutral, it also has 18 electrons. That's what we're looking at for isoelectronic. Now go ahead and take some time, pause the video, work out through these other two example problems, and the answers will pop up here in just a couple of seconds. All right, here's the answers for nitrogen and aluminum. They are both isoelectronic with neon. Again, you're just going until your total from your subscripts add up to the total number of electrons that you have. That's the big kicker. Make sure the totals account for every single electron you have, no more, no less. So even though this is very obviously shorter than orbital spin diagrams, writing electron configurations does still occasionally take time. It's quicker. It still takes a little bit to sit down and do it. The more you do, the faster you're going to get, but especially right now, it still feels like it takes a little bit. There's an even shorter way that we can write all these electron configurations. If we look at neutral aluminum, right, lives at 3s. So we got 1s2, 2s2, or sorry, 3p, not 3s, my bad. 2p6, 3s2, 3p1. And if we look at and compare it to neon, which is 1s2, 2s2, 2p6, we can sit there and say, okay, well, what's the same between aluminum and neon? We can look at these first two energy levels, 1s2, 2s2, 2p6. It's the same. So we can do something called shorthand or noble gas configuration, okay? Which means we can basically take that whole first chunk for aluminum and shorthand it by doing this. We can put the noble gas in brackets to essentially say everything there is the same thing that you would write for neon. Treat it like a checkpoint in the periodic table. Every time you get to a noble gas, you can use that as a starting point if you're doing shorthand configuration. After that, you still have to do the 3s2 and 3p1, but that whole first section is accounted for in the neon. Okay, you can still add up your totals. Just look at neon on the periodic table. There's 10 electrons there. Plus 2 is 12. Plus 1 makes your 13. You always have to use a noble gas. It always needs to be in brackets. And it always has to be one you have passed. Okay, so that's really, really, really important. You have to have passed it in order to use it. So you should always have a noble gas with something else after it. And there's some weird exceptions that we could show you, but for the most part, something like aluminum there, where you can start at neon and then keep going, is what we'd expect to see should we ask for shorthand configuration. Okay, here's a few more example problems. Same deal as always. I'll do one, I'll pause the video, or you can pause the video, work the other two, give it a few seconds, and the answers will pop up. So let's do calcium. Has 20 protons, therefore 20 electrons. There we go. And if I look at calcium, number 20 on the periodic table, the most recently passed noble gas would have been 18, argon. So I'm going to put argon in brackets. And then I'm just going to start reading the periodic like a book from there. Next line down would be 4s, and argon is 18. That means I have 2 left. So there's my shorthand configuration for calcium. Like I said, go ahead and pause the video here. Do arsenic very quickly. Do cadmium very quickly. See if you can get the right shorthand configurations. Okay, here are the answers for arsenic and cadmium. See that, having to draw 33 or 48 arrows, or even still electron configuration writing all the way out from 1s all the way up to 4d or 4p still takes a long time. So having this even shorter shortcut method can potentially save us some time. We will specify exactly how we want to see your electron configuration. So make sure you're reading the directions. We'll ask specifically for orbital spin, in which case we expect to see the arrows. We could ask for regular electron configuration, in which case we do expect to see starting from 1s all the way up. Or we would specify that we want to see shorthand, in which case you need to show a shorthand. So in all of the examples that we've looked at so far, they've all been ground state electron configurations. But when I add energy to my electrons, that excites them. It jumps them up energy levels. So that brings us to this idea of that there are also excited state configurations, something that looks like the below: 1s2, 2s2, 2p6, 3s1, 3p6. So take a second, and I want you to think, why would this be considered an excited state? What looks off? Hopefully you're able to tell that it's that guy right there. It's breaking Aufbau's rule. S1 is not filled, but they've went ahead and moved on and gone up to 3p6. That's what makes this an excited state. Excited states are noticeable because they break Aufbau's rule. But you can still tell me what element this is, from the same way that you could for the ground state. If you add up all your superscripts, your exponents, you still figure out your total number of electrons, and that can still tell you what atom you are dealing with. Well, 2 plus 2 is 4, plus 6 is 10, plus 1 is 11, plus 6 is 17, which tells me that this is chlorine. You can assume that it's an atom and not an ion, but you're just adding up the superscripts, same as normal. So here we have some more electron configurations. If we look at that first one, 1s2, 2s2, 2p6, 3s3, 3p6. Now, it could be ground state, it could be excited state, or it could be something that is impossible. You can't have that configuration. So if I look at this first one, 1s2 is good, 2s2 is good. I filled 1s, then went to 2s. 2s2 is good, filled 2s, then I moved to 2p. Filled 2p, then I move on. But here's a problem. 3s3. Can I have 3 electrons in an s? Remember, s only has 1 orbital, and we know that every orbital can only have 2 electrons, so you can't have 3s3, right? The big issue isn't the 3s, because the 3s should come next. The big issue is that guy right there. You cannot have 3 electrons in an s, so that's an impossible state. You cannot exceed the maximum number per sublevel. Let's look at the next guy, 1s2, 2s2, 2p6, 3s2, 3p4. I fill 1s first. I fill 2s next. I filled 2p, then moved on. I fill 3s and then move on. 3p4, I'm allowed to have 4 electrons in p. It's not full, but you are allowed to have 4 electrons there. Remember, the maximum for a p is 6, which means I followed all the rules. That's a ground state. Every rule is followed. Last but not least, 1s2, 2s2. I filled the 1s, then went to 2s. I filled the 2s, then went to the 2p. I filled the 2p, then went to 3s. But notice how I have s1. I haven't filled 3s before I moved on. It breaks Aufbau's rule. That is the only rule you are allowed to break and still technically have a correct configuration. It just tells you that I'm in an excited state because I've had an electron gain enough energy to jump above where it should start at. Okay, so we've learned about electron configuration, we've learned about shorthand. Now we have to learn about a very particular group of electrons, something we call valence electrons. Now the definition of valence electrons is that they are the highest level, highest energy S and P electrons. So highest energy S and P electrons. They will always be your highest energy level. They're the highest energy level, so therefore they're the farthest away from the nucleus. So they're the ones that are going to be involved in reactions. They're the easiest to get at. That's the electrons that we're talking about, the highest energy level. The S and the P portion of it just comes because those are going to be the ones that are always available. By the time you get to a D or an F, you've already moved on to other energy levels. Before you can get to 4D, you have to go through 5S. Well, hey, 5 is now the maximum energy level, so you don't really care about energy level 4 from there on out. So your sublevels will always be S and P when we're looking at valence. The octet rule says that every atom, in order to be stable, every element, wants 8 electrons in its valence shell. In other words, it wants a full S and a full P. Right? It wants a full S and a full P. In order to have a full S, it has to have 2. In order to have a full P, it has to have 8. So that's where the octet rule comes in. Now, if you have 3 or less valence electrons it's going to be easier for you to lose those electrons and just drop down to the next lowest energy level. Because then, hey, if you have no electrons in energy level 4, then the next highest you have is 3, and that one already is coming full. Because remember, 3 had to be full before you moved on to 4 anyways. If you have 5 or more, it's going to be easier to steal some electrons from another element in order to go ahead and fill up your octet. You're going to fill up those outside p orbitals. So you need to know whether or not these electrons or these elements are going to lose electrons or whether they're going to gain electrons in order to hit that either 0 or 8 mark. This idea of valence electrons and gaining or losing electrons, that's how we determine what ions certain elements are going to make. So I want you to take a second, before we start talking about valence electrons and electrons will it gain or lose or what's the charge, I want you to practice filling out some electron configurations. We have 1, 2, 3, 4, 5, 6, 7, 8 elements here. I'll do a couple of them. Pause the video. You go in and fill out the rest of them, okay? So if we have sodium, sodium lives in the 3s, so I know I have to have a 1s2 that's full, a 2s2 that's full, a 2p6 that's full, and I'm going to end with 3s1. There's my electron configuration for sodium. They get very quick. I promise if you practice, they will really start coming very quickly. Magnesium is one more beyond that. It's still in the 3s level, so I know I have to have a full 1s, a full 2s, a full 2p, and there's your magnesium, 12 electrons, 12 total superscript. Go ahead and pause the video here, fill in the rest of the electron configurations for these 8 elements. Give it a second and the answers will pop up right in front of you. Okay, so here we have all of the electron configurations for all those various elements, all the way from sodium down to neon. Now, when we look at number of valence electrons, we're going to look at the highest energy S and P sublevels. Well, if I look at sodium, I have energy level 1, energy level 2, energy level 3. Hopefully you know the highest number there is 3. So I can ignore everything else except for 3s1, which tells me, hey, how many electrons do I have in 3s? Well, I have 1. If I look at magnesium, highest energy level there is 3. Again, I have 2 electrons, 3s2. When I look at aluminum, highest energy level there still is 3. This time I have 2 in the 3s, 1 in the 3p, which gives me 3 valence electrons. Go ahead and pause the video just real quick and see if you can figure out the number of valence electrons for the remainder of these elements. Remember, highest energy S and P sublevels. Okay, here you can see all of those valence electrons. Arsenic and bromine, those can be some of the trickier examples where notice how you have to ignore the 3D because you already have energy level 4. That's why it's always going to be just S and P electrons. No valence electrons will ever be in the D or F sublevels. So based on the number of electrons, that tells us whether it's going to gain or lose electrons. Remember, it has to get to either 0 or 8, whichever is closest. It's whichever is easiest. So if I only have 1 valence electrons, that atom's options are either lose the 1 and drop to 0, or gain 7 to get up to 8. So it's going to always be easier to basically just round down to 0. So it's going to lose 1. 2, it's going to be easier to lose 2 than gain 6. So it's going to lose 2 electrons. Aluminum is going to lose 3. Carbon's an interesting element because it's equally likely that it's going to lose 4 as it's going to be to gain 4. We don't really give you examples with carbon. We don't make you work any problems with carbon. There's a whole field of chemistry dedicated to carbon and the carbon reactions. It's called organic chemistry. It's all about organic life, which is based around the idea of carbon. And it really comes down to the fact that it can make a whole lot of different bonds with itself, because one carbon could lose 4 while the other carbon could gain those 4, making bonds. That's well beyond the scope of what we're ever going to be doing. But know that it could do either, gain or lose 4. Once we get to arsenic, though, and things with 5 valence electrons, it's going to be easier to gain 3 electrons than it's going to be to lose all 5. So it's just going to go out and it's going to find 3 more electrons. Sulfur is going to gain 2. Bromine would gain 1. Whereas neon already has 8. It's perfectly happy. It's not going to give up any. It's not going to lose any. It's just going to be perfectly happy. It's going to do nothing. So, based on this idea of it gaining or losing electrons, we can predict what the charge of the ion of those elements are going to be. So if I lose an electron, that tells me that I'm always going to have a +1 ion. I'm going to always have 1 more proton than I will have electrons when it turns into an ion. Magnesium would be +2 because I lose 2 electrons. Aluminum would be +3. Carbon could be plus or minus 4. Again, it's confusing. Don't worry about it. We're never going to deal with carbon. But when we get to arsenic, remember, I'm gaining electrons. In other words, I'm getting more negative. I'm gaining more negative things. So it's going to be a -3 charge when I gain 3 extra electrons. Sulfur would have a -2. Bromine would have a -1. And neon is going to have no charge. Since it's not going to gain or lose anything, it's not going to create an ion. Now, ions have very particular names, whether they're positive or negative. If your atom gains electrons to get a full octet, that means it's going to have more electrons than protons. In other words, more negatives than positives. So therefore, overall negative charge. Nitrogen is an example of a negative ion. But all negative ions we call anions. Okay, so know that whenever you hear us use the word anions, we're specifically talking about a negatively charged ion. If an atom loses electrons to get a full octet, in other words, if it has 1, 2, or 3, it's going to have more protons than electrons, so the positive charge is going to be higher. It's going to have an overall positive charge. So magnesium is an example of that. Magnesium forms a +2 all the time. And any positive ion we call a cation. And you can remember that because cations are positive. Yeah, I know. So, anions are negative, cations are positive. This has been a long video. Make sure you're getting your practice in of all 3 kinds of configurations, both the full, the shorthand, and orbital spin. Make sure you're able to understand the difference between regular atoms and ions, and know the different types of charges and names. Anions are negative, cations are positive. Be able to identify valence electrons. All of this stuff is foundational. We're going to be relying on it as we move forward throughout the year. So again, please come see us if you know you're struggling with any parts of all of this, because they all relate together. So if you're struggling with one part, there's probably a good chance you're going to struggle with something else. So please come see us. We will sit down and we will work these out with you.